Hello YouTube and welcome to AP Calculus BC, Chapter 7, Section 4. We're talking more about e to the x and ln of x today, okay? So here we go. So, what if y equals e to the x? What's the derivative? What's dy dx? Well, we've talked about this in the past, and I think we used the quotient, the difference quotient to figure out that it's basically e to the x, but that was an estimate. Can we do this exactly? Let's use logarithmic differentiation. This new thing we just invented, the derivative of a log. All right, what if we take the log of both sides? What's nice about this is that the ln of y equals the ln of e, but the ln of e to the x. But ln and e to the cancel, so you just get x. Now, how do you get dy dx out of this? Well, what if you differentiate implicitly with respect to x using the chain rule? The derivative of ln y is not just 1 over y. Right, we said the derivative of ln of x is 1 over x when you differentiate with respect to x, right? But we're not differentiating with respect to y. Y is a function in x. I don't know what it is. It could be any function of x. Sine x, cosine x, e to the x, it's something else. Y, x squared, whatever y is. I don't know what it is. So we need to use the chain rule here to take the derivative of the inside. So it's like the derivative of ln of u is 1 over u du dx, but it's dy dx. Okay. And the derivative of 1x is just 1, is it not? Okay. And now it's real easy to get dy dx. Remember, y is still e to the x, because we're differentiating the ln of y, but we got dy dx out of that, so we're still talking about y equals e to the x. So how do you get dy dx alone? You multiply both sides by y. But y is e to the x, isn't it? So there's a demonstration that the derivative of e to the x is e to the x, and that's exact. There's no approximations, no limits, no nothing going on here, except for the fact that the derivative is a limit. Okay. So don't forget then that the derivative with respect to x of e to the u is e to the u du dx by chain rule. Okay. And the integral of e to the u du is e to the u plus c by u-substitution. So those two rules we know. All right, let's practice this up. What if y is 2e to the x? What's dy dx? Well, 2 is just a constant multiplier, or dilation factor, so just leave the 2 out of it, and derivative of e to the x is e to the x. Or if you must do the product rule there, the derivative of 2 is 0, will drop out. Eventually get the same thing. Okay, what if y is e to the 2x over 3? Now it's not the derivative of e to the x with respect to x is e to the x. It's a derivative of e to the u with respect to x, where u is a function of x. That's the chain rule. So you get dy dx is what? E to the u times the derivative of u, du dx. If u is 2/3 of x, du dx is 2/3. Okay. How about this one? Y is equal to x times e squared minus e to the x. Well, this is deceptively simple. They're trying to confuse you into trying to do product rule here, but you don't need to, because e squared is a constant, like 2. What if I instead of doing 2x times e to the 2, what if it was just x times 2, or 2x? The derivative of 2x is 2, right? So the derivative of e of 2 times e to the 2, which is another constant, is e to the 2. So the derivative is e to the 2 minus e to the x, is the derivative of e to the x is itself. And just for fun, why don't we check that stuff? Here we go. Let's make a new document. Let's make it a calculator document. And let's do menu, calculus, derivative, not at a point, just plain derivative. The first one we did was, okay, with respect to x, was 2e to the x's, right? Oh, it's stuck already. Look at this. It's crazy. Okay, so 2e to the x. And did we say we get 2e to the x? We do. Amazing. All right, try that again. Menu, calculus, derivative with respect to x of e to the 2x over 3. All right, so e to the, how about rational exponent? 2x over 3, or 2/3 times x if you like. But all right, I'm going to do 2x over 3. And then we get e to the u, e to the 2x over 3, times du dx, which is 2/3. That's it. That's the same thing. And just for fun, here's the third one we did. menu, calculus, derivative. All right, so we had x times e squared. Oh wait, whoops, I'm in the wrong place. Yeah, x times e squared minus e to the x. All right, let's see what you get. And then we said that e squared is a constant, so that's all you get for the first one, and the derivative of e to the x is itself. So we got all the same same results. Perfect. Just checking my work, practicing the Inspire. There you go. Remember, there's only 4 things that you need to be able to do with the graphing calculator on the AP exam. And they are: graph in an arbitrary window. Get a friendly window, get a full graph of your function, whatever you need. Make sure you're showing all the roots and mins and maxes and concavities, changes and stuff like that, whatever you need. And solving an equation numerically, right? Finding a root of an equation where it hits the x-axis on the graph screen. And getting a numerical derivative, not even this, you're not required to do CAS, like we did. This is CAS, Computer Algebra System. Just numerical calculators like the TI-84. So numerical integrals and numerical derivatives. So definite integrals numerically and slopes numerically like this. Okay, all right, here's another question. What if I want to integrate a definite integral from 1 to e squared of 1 over x dx? Well, that's silly because we talked about this yesterday. The antiderivative of 1 over x dx is the ln of absolute x. And we're integrating from 1 to e squared. So you plug in e squared minus you plug in 1. And this is easy because the ln of e to the 2 is just 2 because ln and e to the are inverse functions, they cancel. And the ln of 1, remember, is 0. So you're done. All right, why don't we try that one? Let's see, menu, calculus, integral, yeah. And it's from, what was it now? It was from 1 to e squared of 1 over x. Let's do a rational. 1 over x dx. And you get 2, just like we said. Alrighty, good. More practice. This is just practice now. This should not be new stuff, really. What if I want the definite integral from ln of 2 to ln of 3 of e to the x dx? So that's silly because we know that antiderivative of e to the x is e to the x because the derivative of e to the x is e to the x. And if you plug in ln of 2 and ln of 3, by the fundamental theorem of calculus, you plug in ln of 3 first, then subtract and plug in ln of 2. But don't forget that e to the ln of 3 is just 3, and e to the ln of 2 is just 2, so you get 1. All right, that's sort of silly, but let's try it, just for practice. All righty. Okay, so menu, calculus, integral, and we're going from ln of 2, let's see, second e to the is ln of 2, close it. And then let's go up here to ln of 3, so second e to the is ln of 3, close it. And then it's e to the x with respect to x. And do we get 1? We do. Alrighty, good. Just practicing things up here. Alright, how about this one? What's the definite integral, I did it again, from 0 to 1 of 1 plus e to the x times e to the x dx. All right, so we figured out in class, we didn't record this in class, this is after the fact, that u equals 1 plus e to the x is a nice choice for u if you're doing a u-substitution, because look what du is. Du is e to the x dx, and that's what we got. So this is nice. It's just u du. Power rule, u to the 1 du if you want, right? So isn't that u squared over 2 when you anti-differentiate? Now, unless you want to go back to, in terms of x, why don't we change the limits of integration? When x is 0, plug it in here, e to the 0 is 1 plus 1 is 2. When x is 1, e to the 1 is e plus 1 is 1 plus e, whatever that is. Whoops. Alrighty. And so we get u squared over 2 evaluated from 2 to the 1 plus e. So it's 1 plus e squared over 2 minus 2 squared, which is 4 over 2, is 2. Unless you want a decimal equivalent or FOIL it out or something, there you go. Alrighty, so let's check that one out. Here we go. Menu, calculus, integral. Alrighty, now that one was going from 0 to 1, so 0 to 1 of quantity 1 plus e to the x. Close it. Well, not there. There. Times e to the x. And I don't know if I can use an implicit multiplier here. Gotta be careful. I think we can because of the parentheses. And put the x over here. And our answer was 1 plus e quantity squared over 2 minus 2. I don't know if they'll write it in that format. Maybe they FOIL it out. Let's see what we get. Well, is that the same thing? E squared over 2 plus e minus 3 halves? Probably. Let's find out. Let's see. Let's FOIL this 1 plus e squared. So 1 plus 2e plus e squared all over 2 minus the 2. All right, so let's see. Let's do this by highest degree first, okay? E squared over 2 is e squared over 2. 2e over 2 is just e. And 1 half minus 2, or 1 half minus 4 halves is negative 3 halves. Yeah, that's exactly what we got on the calculator, isn't it? Wow, look at that. And if you want a decimal, what the hey, there it is. 4.913 if you want, okay. Roughly, I put a dot here when I'm rounding off, 4.913, unless they tell me different, I round off to 3 places. All right, that was good. Just practicing up e to the and ln and calculator stuff. And here we go. All right, here's an indefinite integral. Please ignore the bell. We're in a weird bell schedule today. What if I wanted to integrate e squared cosine e to the x? Now this looks a lot like an integration by parts. We haven't done that yet. We will pretty soon, which is like a product rule for integrals. Well, but it isn't. Because if you choose u is e to the x, then du dx is e to the x, bring up the dx, right? So du is e to the x dx. So I have e to the x dx here, and I have e to the x dx here. So this is simply cosine of u times du. And you know the antiderivative of cosine u, it's sine u, isn't it? Because the derivative of the sine is the cosine. And since we're not doing limits of integration, I might as well go back to x since we started with x, and u is e to the x. And of course, you can always check this by differentiating sine of u, and you'll get cosine u du. It works out. Nice. And just for fun, practicing the calculator stuff. Now let's do an integral without bounds, right? So menu, calculus, integral. Don't fill in the bounds. And it was, what was it? It was e to the x. No. E to the x. And then get out of the exponent times the cosine of e to the x. Alright, let's get out of that exponent. Let's close that parentheses. Let's put it in with respect to x. And we ended up with sine of e to the x plus c, right? And there you go. Of course, you know that Castiel, or the TI-inspired CX Cas, does not do the plus c stuff. All right, nice. Very good, very good. All right, how about a derivative? Take a look at this. What if, just a lot of practice problems today, y equals the ln of, if y equals the ln of x, the derivative is 1 over x, right? If y equals ln of u, the derivative is 1 over u du dx. Well, here's your u. Have fun. This was sort of a beast. Okay, so 1 over u, this is u, right? Du. So 1 over u, we're going to multiply by du. How about we multiply the numerator, the 1, by the derivative? Let's do it. Low, d high, minus high, d low, all over low squared. I forgot the song, but there you go. I forgot the tune. But that was the song we used to sing, right? All right, and so let's simplify this stuff. The numerator, this is a complex fraction. So the top fraction, the numerator, its numerator is simply -1, isn't it? Now, how do you divide by that denominator? The denominator is a fraction, x over x minus 1. How do you divide by a fraction? You never do. You multiply by the reciprocal. And so what happens? The x minus 1 is reduced. So you get -1 on top and x times x minus 1 on the bottom, and there's your derivative. Now, what does that mean? If you integrate this answer, you should get ln of x over x minus 1. That's hinting at a quotient rule that we don't know for integrals, antiderivatives, too, called integration by partial fractions, which we'll get to pretty soon also. But let's just check that out. Let's see. Let's go on the calculator and try it on the calculator. All right. Again, don't forget about on the exam, on the AP exam, there's 4 parts technically. There's 2 part 1s and 2 part 2s, right? Only the middle 2 parts, part 1b and part 2a, allow you to use the calculator. And I think they also changed part 2 in that there's only 2 free response questions in part 2a, and now there's 4 free response questions in part 2b. It used to be 3 and 3, now it's 2 and 4. So it's less calculator based than it used to be. Okay? All right, so roughly half the exam is calculator based, but you actually have an extra free response question. And again, forget the bell. All right, so what are we doing? We're taking the derivative. All right, so menu, calculus, derivative not at a point. All right, with respect to x of ln, second e to the, and it's a quotient, x over x minus 1. Okay, x over x minus 1. All right, and close the ln. And do you have to close the derivative? I guess that's probably it. All right, enter. And there is the exact same answer, -1 over x times x minus 1. I'm curious, what if, and again, see the yellow thing? That means that the answer is not unique. There's a lot of different ways you could have written it, or a lot of different ways you could have done it and got a different answer, but the derivative should give you the same slopes of the tangent lines along the curve at the same points, right? So you could always check that the graph of your derivative matches the graph of the calculator's derivative and see that they overlap, in fact, right? How about if I integrate that? Could I go menu, calculus, integral, without limits of integration of, can I get out of here? Let me get out of here. That. Can I copy that into it? No, I can't, can I? How would I do that? I guess I have to type it out? There's no way to cut and paste it directly? Wait, listen. Menu, calculus, integral. No. That's a pain. There's got to be a way to cut and paste it. Hang on. Wait, all right. Control, delete is clear that one, right? Okay. All right, what if I do menu? The simulator is a little bit clunky because it doesn't have all the mouse attributes that the real handheld has. So I'm trying to figure out how to do this on the emulator. Sorry. Hang on. All right, we're doing that, right? But I want to cut and paste this. No, not there, though. What am I forgetting? I'm forgetting how to do this. All right, forget it. Let's just type it in. It's fun. All right, so rational, -1 over x times x minus 1. I mean, that was pretty easy to do in the first place. Why don't I just do that? And can I get away with implicit multiply there? Well, we'll find out. Because the antiderivative should be the ln of x over x minus 1, right? Let's see what we get. Invalid imply multiply. All right, so I got to put the multiplication here. Because it thinks that's a function. X of something, right? Don't do that. All right, enter that. What the heck? Well, that's a domain issue. Forget the absolute value for a minute. But remember what the -1 in front of the ln means. That's -1 times ln, right? So that could be put into the ln as an exponent. So if you take the x minus 1 over x to the negative 1, isn't that the reciprocal of x minus 1 over x is x over x minus 1? Yeah, you're getting basically the same thing except for the domain issue. We'll get to the domain issue when we talk about differential equations. It's easier to talk about there, so I'm not going to worry about the domain issue. You'll note that most of the problems we did today, all the x values were positive anyway, so the absolute value thing didn't really matter. So I'm not going to go there yet. We will. Okay, what else did we do? Oh, this one's fun. Take a look at this. Can you figure out the area from 1 to a under the curve ln x dx plus the area from 0 to ln a of e to the y dy? Now the second part's easy because the antiderivative of e to the y dy is just e to the y, and then you plug in ln a, and you plug in 0, and you get stuff. Okay, but the first part, we don't know the antiderivative of ln x yet. We know the derivative of ln is 1 over x. We don't know the antiderivative of ln. Okay, so what do you do? Well, what we did was we graphed it by hand. Look, graph ln x. It looks like this, right? This is where x equals 1. That's x equals 1. Let's say this is where x equals a. Greater than 1. Right? A is greater than 1. Like I should have said that. All right. Okay. Now, do you see that if you take vertical strips here, your Riemann rectangles have a height of ln of x and a thickness of dx, and isn't that the first integral? That area right there? That's the first integral. Okay, well I still don't know what it is, but that's okay. But now look at this. If you plug in x equals a into this curve, what's the y value? Isn't that ln a? All right. So look at what they gave you. They took the integral in terms of dy. So in other words, horizontal strips. The thickness is in dy. What's the height? Now look at it sideways. The base of the rectangle is the y-axis, and the height hits the ln of x curve, right? But that height, that's an x value. So how do you get x alone in here? What if you raise both sides as powers of e, and e to the ln of x is just x, and x is e to the y, right? So the height of that rectangle, the horizontal rectangle, think of it as the height from the y-axis to the curve, is e to the y, and the thickness is dy, and that's the second integral right there. So what if you add up those two areas? Right? You're adding up this area and now this other area over here. Let's see. I'm going to draw it. This other area over here. Don't you get a whole rectangle? This rectangle right here? Well, that's easy. What's the area of a rectangle? The base, which is a units, times the height, which is ln a units. So you get a ln a. Ta-da! Is there a way to do that analytically? Yeah, if you know that the antiderivative of ln of x is x ln of x minus x. But we did it that way. And we got an exact answer. No approximations, no nothing. Could have done it on the calculator, I suppose. But look, how about this? Let's do it analytically. What is the antiderivative, the definite integral from 1 to a of ln of x dx, given that the antiderivative of ln of x is x ln of x minus x, which we will figure out down the line as a by parts. This is like a product rule where one factor is ln of x and the other factor is dx. And then we add on to it the area from 0 to ln of a under e to the y dy. And let's see what we get. All right, so we're going to plug in a and 1, right? Then we're going to add on the antiderivative here is e to the y, right? So we're going to plug in 0 ln a. Let's see if we get the same answer, which was a ln a. Plug in a, plug in 1 and subtract, fundamental theorem of calculus, part 1. All right, that whole thing we're going to add to the e to the y area. So you get e to the ln of a minus e to the 0. All right, so simplify stuff. Ln of 1 is 0. So this is 0, minus 1 is negative 1, and subtract it, you get positive 1. But this is 1 also, right? So aren't you adding a negative one over there and a positive one over there? They cancel. All right. What about e to the ln of a? That's just a. You're adding a on the end there, and you're subtracting a over here, aren't you? So look, everything cancels but a ln a. Ta-da! So there's an exact analytic result there too. Alrighty. What if we punch that into the calculator just for fun? See what happens if we throw that in the calculator. Alright, let's see. How about we do menu, calculus, integral, from, let's see if I can put in literal values here. Oops, I got stuck again. What if I put an a in here? Will I be able to do this way? And then it's ln of x. Just for fun, how much is that? That's the a ln of a minus a plus the 1 we were talking about before. Right, okay. Now I want, all right, so it worked with the a. Good, that's nice. Now I want the other integral. Menu, calculus, integral from 0 to ln a. Okay, so from 0 to ln of a under the curve e to the y dy. And remember, we wanted to add those two results, so that's clearly the a's cancel, the 1's cancel, you get a ln of a, right? That's it. Or why don't we just do this? There you go, perfect. All right, so one more question. Remember where we started. Didn't we start with this? If y is e to the x, the y dx is e to the x also. But what if it's not e to the x? What about another exponential, like 2 to the x, 3 to the x, 5 to the x? What happens then? Let's find out. There you go. All right. Let's do the exact same process. So if y is a to the x, let's do logarithmic differentiation, ln of both sides. Then differentiate implicitly with respect to x. I did something wrong. Whoops, sorry, back up. Went a little too fast. ln of both sides, here we go. There you go. Don't forget the ln of a to the x is x times ln of a, right? Where ln of a is some constant. Alrighty. Prior to that, it was e to the x, so ln of a would have been ln of b is 1, so that's what we had before, we just had x. All right, now differentiate. So 1 over y dy dx is equal to ln of a, because again, that's a constant multiplying x. Like if you're differentiating 2x, you get 2. Well, we're differentiating ln of ax, so we get ln of a, because it's a constant. Or do product rule if you must. It's a lot more work for nothing. All right, get dy dx alone by multiplying both sides by y, and you get ln of a times y, but y is a to the x. Alrighty? So, for example, what if I gave you y equals 3 to the x? What would be dy dx? It would be 3 to the x times ln of 3. That's what we're saying. So that's like a little fudge factor. Now, if it's not e to the x. If it's e to the x, it works too, because then you get e to the x times ln of e, but ln of e is 1. Okay. What if I wanted to integrate 3 to the x? What about that? Well, let's see. Let me guess. What if I guess 3 to the x plus c? How do you check that? You differentiate your antiderivative. You better get back your integrand, right? But if you differentiate 3 to the x, you don't get 3 to the x. You get ln of 3 times 3 to the x. It's off by a factor of ln of 3, so fix it. So now you know how to differentiate any exponential, no matter what the base, not just e to the. And you know how to anti-differentiate any exponential, no matter what the base, not just e to the. There you go. So it's a fudge factor of multiplying by the ln of the base when you're differentiating and dividing by the ln of the base when you're anti-differentiating. And that's all she wrote. Well, I don't know. Maybe we should check that on the calculator just for fun. Alrighty. So what if I want menu, calculus, derivative, with respect to x of 3 to the x. Let's see what you get. Like we said, ln of 3 times 3 to the x. And what do we say? Menu, calculus, integral of no limits of integration, just an antiderivative or indefinite integral of the same thing, 3 to the x with respect to x, and you get, just like we said, of course, remember that the calculator doesn't give you the plus c stuff. All right, perfect, that's it. So we're done for today. That's all we talked about today, except I added a lot more calculator work just for fun, just for practice. And hope that was helpful. That was section 704. Bye-bye, YouTube. Have a nice day.